In this video, we're going to use integrals to calculate work. When we talk about work in this section, we are talking about the physics idea of work. That is, work that is done when a force applied to an object is moving that object. So for example, if you take some object on a table and you start pushing that object across the table, then work is being done. Work is going to involve both the force it takes to push the object and the distance that you push it. When we deal with a constant force, in other words, I'm applying that force as a constant pressure over a specified distance, then work is calculated by just multiplying that constant force times the distance. So if I'm pushing an object across the table at a steady force, then I multiply the force applied to that object times the distance that that object is moving. With this, the idea of work has some interesting units. Because it's a force times a distance, we end up with units that are combinations of forces and distance. Now, the standard international unit of force, or one standard international unit of force, is a Newton. It's kilograms per meter per second squared. Again, that's just a Newton. And if I apply that force over meters, because we're using meters here, then the standard international unit of work is a Newton meter. So it's that force applied over meters. So that's a Newton meter. And that's often just said, we call that a joule. So a Newton meter or a joule is a standard international unit of force. There are other units of force of work as well. I misspoke. So the Newton meter is a unit of work. The Newton is a unit of force. There are other units for work as well, and most of these are hyphenated because it's a force hyphenated with a distance. It's like force times distance. So for instance, another common unit is foot-pounds. You apply a force of pounds over a certain number of feet, and that gives you foot-pounds. So our units of work are often these hyphenated: Newton meter, foot-pounds. You could do mile-pounds or mile-tons or any types of distance and force combined. Now, all of this is really nice when we have a constant force being applied. But in real life, oftentimes the forces that affect objects are changing. If a force changes over the distance that I am applying that force to it, or applying a force to it, then basically we can approximate the total amount of work with small amounts of force times small amounts of time. So we take small force chunks over certain distances that are going to get really, really short. And as we take the limit, as those distances get shorter and shorter and shorter, then what we're going to end up with is essentially an integration. Imagine that the y-axis is giving me the force, and the x-axis is measuring some sort of a distance. If I have a force function, then I could graph it in the xy plane. And then work, since work is force times distance, we can approximate that with the small chunks that I was talking about. And essentially, the total work becomes just the area under the force function. This is the formula for work if the force being applied is variable. So if an object is moved along a straight line by continuously varying force, we call that F of x, then the work done by the force as the object is moved from point A to point B, that is x value of A to x value of B, is just the definite integral of the force function evaluated from A to B. So a work formula is just a definite integral of a force function. By the way, if our force function is constant, this also works because when you integrate a constant function, you get that number times the difference between A and B. So whether the force function is constant or the force function is variable, we get this formula to calculate work, which is again just the definite integral of the force function. It's a pretty easy integration to do once we know what the force function is. And that's really the toughest part about any of these problems that we're going to do is finding the force function. We're going to use a couple of different pieces of information. One piece of information that we can use to find a force function is that the gravity constant or the gravity acceleration rate is 9.81 meters per second squared, if we're talking about in meters, or 32.2 feet per second squared, if we're talking about feet. So if I'm lifting something off of the ground, then gravity is going to be affecting it, and those two numbers will come into play. Another thing we should know about in a different context, there's a couple of other force functions that are common that we'll use. One of them deals with Hooke's law, and that is the force it takes to compress a spring is going to be some constant times the distance that it's already compressed from its natural position. So the force used to compress a spring is a constant times d, where that d is distance from its natural place. By the way, this law, that is Hooke's law, it also applies if you try to pull a spring apart. So if I have a spring and I'm trying to compress it, I have Hooke's law. If I have a spring and I'm trying to pull it and stretch it out, then I can also use Hooke's law. So if I'm either compressing or pulling it apart, stretching it out, we can use that same formula. Another formula with force is that Newton's law of universal gravitation. It says the force of gravity is going to be some constant times m1 times m2. That's the mass of object 1 times the mass of object 2 divided by the distance squared. That distance squared is the distance between the two objects. So the force of gravity between the Earth and the moon can be calculated using this. And if the moon all of a sudden got smaller, that would be changing the mass, so the gravitational force would change. If the moon suddenly got further away, then this distance would change. So that's Newton's law of universal gravitation. There are a lot of other force functions as well, but in this section for this class, we're just going to stick to these and we'll be just fine with these. So these are the ones we're going to use in this section. And obviously there are other ones you can use as well if you go into other realms of physics. So let's do an example. Let's imagine that there is a rope hanging off the top of a cliff. The rope is going to have a mass of 1 kilogram per every 4 meters. So 1 kilogram per every 4 meters. How much work is performed in pulling the rope up to the top of the cliff? In this example, we're not talking about a spring. We're not talking about universal laws of gravity. Basically, we're talking about as I pull the rope up, how much force do I need to apply at each point? If 100 meters of rope is hanging down, then the rope is going to feel heavier and it's going to take more force to pull it up. If only 20 meters of rope is left, then the rope is going to feel lighter and it's going to take less force to pull it up. So the force function for pulling up this rope is going to be variable and it's going to be determined by how much rope is hanging still off the top of the cliff. So here's a real crude drawing. We have a rope hanging off the side of a cliff and I'm pulling it up. Now, I can, in this problem, call X 2 different things. I could, if I wanted to, let X be equal to the amount of rope that is hanging. Because as I start to pull this rope up, I will start at 100 meters of rope. And as I pull it up, let's say I pull up 20 meters, then 80 will be left. If I want to do it the other way, I can also say let X my variable, so this is my or, I can let X be the amount of rope I've already pulled up. So at the start, if X is the amount of rope I already pulled up, I'd be starting at 0 because I've pulled no rope up. And 100 would be hanging. At X of 20, I would have been pulled 20 up and 80 would be hanging. On the other hand, if I use the other version, X being the amount of rope hanging, when I start, 100 is my X. And as I pull 20 up, then 80 would be hanging. So whichever way you want to do this is okay, but we are going to end up setting up our integration different ways depending on which X you choose. I think what I'll do is I will let X be the amount of rope that has been pulled up. So here we go. Now I'm ready. X is going to be equal to the rope pulled up. Now, if I do that, then my force function is going to be, well, since all these things are in meters and kilograms, my force function is going to utilize the constant of gravity, that is 9.81 meters per second squared. Again, we're using meters here. And I'm going to multiply that times the amount of rope hanging. Now, if X is the amount of rope that I've pulled up, then the amount of rope hanging is 100 minus X. Now there's one other thing I need to multiply by. The other thing I need to multiply by is the weight per meter. If 1 kilogram is the weight for every 4 meters per rope, excuse me, then that means 1/4 of a kilogram is the weight per meter. By the way, oftentimes you can kind of check what's going on here by using the labels. The gravity constant is in meters per second squared. The weight per meter is kilograms per meter. And then this is how many meters of rope is hanging. So that's in meters. If I multiply all of those labels, you'll notice that what we get is a meter times a kilogram on top, because these 2 meters will cancel out. And we will have to multiply times a second squared on the bottom. And that is my unit for newtons. So I do get a force here in newtons if we look that back up. I had wrote kilograms times meters per second squared. Obviously, you can change the order of kilograms and meters if you'd like. But kilograms times meters per second squared, that is our Newton. So we do know we are getting a force in that force function. And again, we can also think about it as just common sense. We have our gravity constant times the weight per meter times the number of meters that the rope is hanging down. Now we're ready to find the total work that will be done. If I want to find the total total amount of work that's being done, then we're going to integrate. Now, X is the amount of rope pulled up. I'm going to start with 0 meters of the rope pulled up. And I'm going to pull up the rope all the way to the top. At the top, I will have 100 meters of rope pulled up. So we'd be integrating from 0 to 100. Like we said, that force function is 9.81 times 1/4 times 100 minus x. So I'm going to write that in as 9.81 over 4 times the quantity 100 minus x. That's what I'd be integrating to find the work done in performing this task. You can do this by hand if you'd like, but I'm going to just type it into my calculator. When I type that into my calculator and did the calculations, I got that the amount of work that was done is 12,262.5. Again, this would be in Newton meters or joules. When I say or joules, joules is the same thing as Newton meters, so I don't want to confuse you there. So our force was in newtons, our distance was in meters, so we had Newton meters, which again is called joules. I'm not going to ask people to label things and have like the precise labeling, but every time I do a problem, I will put the labels in so that you can see what kind of labels we're getting there. Now I said that this is the way we do it if I let X be the amount of rope that I pulled up. What if I let X be the amount of rope that is hanging down? The force function is still going to be 9.81, that's the gravity constant, times the weight per meter of rope, that's 1/4 of a kilogram per meter. But now I times it by X because that is the amount hanging. When I go ahead and rewrite my force function, I would get 9.81 over 4 times X integrated. And obviously, we're going to integrate the amount of rope hanging varies from 100 meters hanging to 0 meters hanging. If I want to get a positive value, then I actually start with the 0 and end with the 100. Because otherwise I get a negative work being done. So if I want a positive work being done, I start at 0 and end at 100. Okay, so the amount of rope hanging changes from 100 to 0. But again, this integration order gives you a positive value. So there we go. 12,262.5. Again, this is in joules if we're dealing with that. Newton meters, which are joules. Because of this kind of weird thing with the integration where I started at 0 and ended at 100, that's why I kind of like X to be the amount of rope pulled up. I like this method better because it makes more sense to me that if you start at 0 meters pulled up and then you end at 100 meters pulled up after you've pulled up the whole thing. So I kind of like this setup a little bit better. It makes more sense in my integration bounds to me. Example 2 is similar. It says a 10-meter chain is lying on the ground or laying on the ground. We wish to lift it up until the point where it's no longer on the ground. So as I start to lift the chain, more and more and more weight is going to have to be lifted. Let's say the chain has a mass of 2 kilograms per meter. How much work is performed in lifting the chain off the ground? So lifting the chain up until we have a point where all of the chain is in the air. This one is pretty straightforward. Again, we have a chain on the ground. We're lifting it straight up. I think of this as, think of like a crane holding on to this, and we're trying to lift it up, or some other type of object holding on to this, and I'm trying to lift it up. Some of it's going to be on the ground. There's a relationship between how much is in the air and how much is on the ground. So if 2 meters are in the air, since the chain is since the chain is 10 meters long, then 8 meters is going to be on the ground still. If 8 meters is in the air, then 2 meters is going to be on the ground still. So the amount on the ground and the amount in the air have to add up to 10. I'm going to let my X here be the amount that is lifted, the amount of the chain that is lifted in the air. If I do that, then the force function is going to be my gravity constant times the weight of the chain that is per meter. So we're 2 kilograms per meter times the amount of the chain that is in the air, because I won't feel the weight of the chain that's on the ground yet. I only feel the weight of the amount that's in the air. So that's it. That's the whole thing. Force function is 9.81 times 2 times x. And obviously, if the entire chain is lying on the ground, we're starting at 0 as the amount lifted in the air. And we're ending when the entire chain gets lifted off the ground. So when all 10 meters is in the air. 9.81 times 2 is a 19.62. This is very easy to do by hand if you'd like. I think I'll still use my calculator just because it's a little bit quicker. I end up with 981. Again, this is in Newton meters because we're talking about kilograms and meters, and 9.81 as my gravity constant. Again, when we're talking about gravity constant, we're talking about meters, kilograms, all that kind of good stuff. Well, technically just kilograms. So 981 is my final answer. That's how much work is done. Again, that work is in Newton meters or joules. And that's how much work is done in lifting the chain from the ground to the air. by the way, in this case, my force function is just a linear function. So if I were to graph that, what I would be looking at is just the area under this straight line between 0 and 10. This is has such a steep slope of 19.62 that sometimes it's hard to see graphically, but all we're really doing is calculating this area here, this area underneath my force function between 0 and 10. And we got that that area was 981. Okay, so the work done was 981 joules. Let's do another example. Let's do an example with a spring. So a force of 1,500 pounds is what it takes when compressing a spring 3 inches from its natural length of 15 inches. So basically, we've compressed the spring down 3 inches from its natural length. So imagine holding a spring and compressing it. Let's in fact think of holding a spring on one side that's fixed and you're pushing on the other side. Once you've pushed that spring 3 inches, you are to hold it there, you're applying a force of 1,500 pounds. So that's what it's saying. Let's find a force function for this scenario. Now, I like to draw things, and orientation is kind of important. So when I'm compressing a spring that's 15 inches long, I'm going to think of it as starting sort of at the origin. And then the spring is going to go, I know this is a poor drawing, but going to go all the way. Ooh, that's really poor drawing. Down till it hits 15. So think about anchoring the spring at 15, and we're going to compress in that direction. Now, that means that if I am starting at 0, an x of 0, then I have compressed this spring 0 inches. As I move to the right, let's say I'm down here at x equals 3, then I have compressed the spring 3 inches. So the spring is sitting on this x-axis, and I'm compressing it to the right. If I do that, whatever value of x I am at gives me how far I've compressed the spring. And that turns out to be a really nice feature. The reason that is a nice feature is because Hooke's law says the force that it takes to compress a spring d inches is some constant times your rate of compression. If I want to write a force function with x as my variable, if I orient the spring the way I did in the picture, x is equal to the amount that it has been compressed, and therefore my force function can be just some constant multiplied times x. Now we try to find this constant, and this is what this information is telling us. It says a force of 1,500 pounds is what's going to happen when we've compressed 3 inches, and therefore 1,500 is equal to my constant times 3. That means dividing both sides by 3, obviously. That means my constant is 500. Now I know that the force function in this scenario is going to be f of x is equal to 500 times x. That's my force function. And now if I'm doing any other compressions with this spring, in order to find the work, I can find the work by using this force function. That's what we're going to do in the next part of example 3. Obviously, finding the force function was part A of example 3. Now let's say we want to find the work done in compressing the spring down 5 inches from its natural length. So that means starting at its natural length and compressing down 5 inches. It's pretty straightforward that since x is the amount I compress, that means natural length means that x is 0. Down 5 inches goes to x equals 5. So if I want to find the work done, all I have to do in this case, compressing the spring down 5 inches from its natural length means I start at natural length and I go to 5. So I start at 0 and I go up to 5. And my force function is just 500x. Again, if you wanted to, this is a pretty straightforward thing to integrate by hand. I am going to use my calculator to do this. Very easy to type in with a calculator as well. So integrating 500x with respect to x gives you 6,250. Now this is not going to be in joules because we're talking about inches and pounds. So this would be in inch pounds as my label. If I wanted to convert that into foot pounds, I could, knowing that there are 12 inches in a foot. So if you wanted to convert it to, instead of from pounds to tons, you could do that. Just multiply times some pound to ton conversion. 2,000 pounds is 1 ton. So if you wanted to convert it into some other label, you could easily do that. But there we go. That's how much work is done in compressing the spring down 5 inches from its natural length. One thing we have to be careful of when compressing the spring is the wording of the problem. Let's do 2 more examples with compressing the spring. In the first of the extra examples, so in example what I call 3C, it says find the work done in compressing the spring down to a length of 8 inches. And then in the last one, it says find the work done in compressing the spring from a length of 12 to a length of 6. We're using the same spring. This is the same spring that we found the force function of in part 3A. So same spring, same force function. In the first, in 3B, We looked at compressing the spring down 5 inches from its natural length. Its natural length had a compression of 0 down 5 inches to 5. If we say find the work done in compressing the spring down to a length of 8 inches, again, this is implying from its natural length. Then what we would be doing is we'd be starting at 0 again. But when the spring is 8 inches long, since the spring at its natural length was 15, that would be a compression of 7. So be careful with the language here. Down to a length of 8 inches means 7 inches of compression. So remember, the spring is 15 inches long. If we're going to have a spring that is compressed down to a length of 8 inches, that means the distance from here back needs to be 8 inches. So this, we're going to compress it from left to right until it's this length. And that is a compression of 7, obviously from 0 to 7. And when we calculate that, we get 12,250. Notice, again, that's going to be in inch pounds. Notice that going from 0 to 5 only forced us to have 6,250. That almost doubled in going that extra 2 inches. Because after you've pressed the spring in, it gets harder and harder and harder to compress more. And so going from 0 to 7 was almost double the work in going from 0 to 5. Now we can also ask something like 3D, which said find the work in compressing from a length of 12 inches to a length of 6. So we've already compressed it from its natural length to 12, and I want to know how much more work going from 12 to 6. Remember, a length of 12 means we started already at a compression of 3. A length of 6 means that we've went a compression of 9, because again, how much you compress is just the length of the spring, which is 15 minus the current length. So the original length of the spring, 15 minus current length. So if we're at a length of 6, I just do 15 minus 6. That's a compression of 9. This integration is easy to do either by hand or calculator. I ended up with 18,000 inch pounds. Some people may put pound inches, but I'll put it as inch pounds. That's a little bit more common. So 18,000 inch pounds. Again, we see that this is just a compression of 6, and it took more work to do that 6 than it did to do this first 7. And that's because as you push the spring in, then it becomes harder and harder and harder to push in more. Again, be careful on the reading. This is not from x equals 12 to x equals 6. This is length of 12, which is x of 3, to a length of 6, which is an x of 6. Or excuse me, x of 9, excuse me. So not an x. Length of 8. Here, compressed down 5. Again, you have to be very careful about the language in these problems. Let's take a look at another example. This says a force of 12,000 newtons stretches a spring 100 centimeters from its natural length of 2,000 centimeters. Find a force function for this scenario, and then we'll calculate some work in the next couple of parts of example 4. In this case, we're stretching the spring, and so I want x to be the amount that I stretch the spring. A lot of times I'm going to think about this as the spring laying on the left-hand side of the y-axis, and therefore x is the amount that I stretch the spring. So on the graph, basically I let my spring be along the x-axis, but to the left of the y-axis. And I'm going to pull that spring. If I'm stretching it out, I'm going to anchor it over here. Now I can't expand, but I'm going to anchor it over here, and I'm going to pull it to the right. Okay, I know I don't have my numerical values correct, but that's the idea. So x is going to now be the amount that I stretch this spring. I don't like to draw very well on my own, so if I'm drawing on the board, it looks a little bit better, but and on the computer, it doesn't look that great. My drawings don't look very good at all. Okay, so anyways, my force function is going to be, let me call that capital F because we've been calling everything else capital F. My force function is going to be some constant times the amount that I stretch. And if I orient my spring the way I did, then the amount that I stretch is just an X value. It says the force of 12,000 newtons stretches the spring 100 centimeters from its natural length of 2,000. So its natural length is 2,000, but the amount of stretch is 100 centimeters. That means my constant is going to be 120. 12,000 divided by 100 is just that 120. So my force function is f of x is equal to 120 times x. The information in here allowed me to determine my force function, and now I'm ready to use that force function in order to calculate work. So let's try these two things. Now, if you want to try these on your own, again, push pause on the video, and in a couple of seconds, I will do these on the video. So we want to find the force function in stretching the spring 600 centimeters. Let me rephrase that. We want to find the work done in stretching the spring 600 centimeters from its original length. Then we want to find the work done in stretching the spring from its original length to a length of 3,200 centimeters. Notice that this is an amount of stretch and this is a final length. So we have to be, again, careful about my bounds. We'll do both of these. So stretching the spring 600 meters from its original length. Again, X is the amount of stretch. So we're going to start at the original length, that is 0 stretch, and then 600 centimeters worth of stretch will be my final bound, which is the B. We already know that my force function is 120 times the amount of stretch. When I do this and I integrate, I end up with a really, really large number. 21600 and then 000. So what is that? It looks like 21,600,000. This would not be Newton meters. This would not be joules because we're dealing with centimeters here. So we're dealing with newtons and centimeters. So it would be Newton centimeters as the label. If you want to convert that to Newton meters, you can. Just take into account that there are 100 centimeters in every meter. So you could just multiply times 1 over 100, and then you'd convert that to Newton meters or joules. I don't ask people to do that. I just leave it as is. In a similar way, we can calculate the work done in stretching the spring to a length of 3,200 centimeters. Again, this is implied, it's from our original length. So that means from 0 stretch, remember that the original length of this spring is 2,000 centimeters. So if it starts at 2,000 and we stretch it to 3,200, that means the amount of stretch is 1,200. So my bounds are going to go from 0 to 1,200. We integrate the force function from 0 to 1,200. Again, you can do this by hand fairly quickly. I tend to always use my calculator just because of the speed. And in this case, we get 86,400,000 Newton centimeters. So these are the numbers that we get. 21.6 million and 86.4 million Newton centimeters. That's the amount of work that you would have to do to stretch such a spring. Now, before we go through this, um, obviously I have these numbers that are completely made up. If you actually had a spring that it took 12,000 newtons of force to stretch out 100 centimeters from its original length of 2,000, you might have a ridiculous looking spring. Okay, So these are definitely made up numbers, and you probably wouldn't see a spring like that. This is a lot of joules of force. Obviously, Newton centimeters are not the same thing as joules, but if you divide by 100, you get joules. And 15 joules is what it feels like is apparently hitting your hand against a wall, like kind of punching a wall in a moderate fashion. So this would be a lot in the way of work. And obviously so would this. But even though this spring probably does not exist in real life, you can still do the calculations. We can still come up with the actual numerical values. Let's do a couple of other examples where we have to find a force function. Here we have the first part of example 5. Let's assume we have some sort of a space module that weighs 15 tons on the surface of the Earth. So this really heavy thing that we got to shoot out into space. We want to find a force function for propelling the module away from the Earth. And the radius of the Earth is close to 4,000 miles. So we will use 4,000 miles as the radius of the Earth. It's not exactly 4,000 miles, but it's close. So we'll use 4,000 miles as the radius of the Earth. And we want to find a force function. Now, in this scenario, let me go back to in this scenario, we're going to be using the force function of Newton's law of universal gravitation. The two objects that we're talking about here are the space module as one object and the Earth as the other. The space module and the Earth have fixed masses, and this constant will be fixed. So really, the numerator of this force function is just one big constant determined by a number of different factors. The two masses that were involved and the constant there, the constant of gravitational attraction. And then the variable is going to be this d squared. D is the distance between the two objects. The information that I need is that the space module weighs 15 tons on the surface of the Earth. That is giving me a force of gravity while this space module is on the surface of the Earth. And we measure the distance between the module and the Earth not by where it's at on the surface, but rather the distance between the module and the center of Earth's mass, which would be 4,000 miles into the Earth. Let me draw it out here. So I pretend that the Earth is basically a perfect circle here. And what I'm going to do is I'm going to put the space module right here on the surface of the Earth. Notice that the distance between the space module and the center of mass of the Earth is actually 4,000 miles. The way I'm going to project the space module out is I'm going to project it out in this direction. So I take this space module, whatever it is, and I project it out away from the Earth in that direction. Okay. So X is going to be how many miles away from the center of the Earth that I am. And we're going to start out eventually at 4,000 miles away from the center. Now I have enough information to create my force function. Again, force function is K, gravitational constant, times mass 1 times mass 2. But all of those things, the mass 1 times mass 2, are constant. So what I do is I say my force function is actually one constant number. I'll call that capital C for now, or maybe you could call it capital K, over x squared, where my x is distance between the space module and the center of the Earth. So x is that distance, and there we go. We know that we get a 15-ton force when the distance between the center of the Earth and the space module is 4,000 miles. So I take 4,000 squared times 15, and that will give me the constant that I'm looking for, which is like 240 million. Now, that's a really big number, but again, makes sense. And that means my force function is equal to 240 million divided by x squared. And that's the thing I'm going to be integrating when I find work. So this is my force function. I got that by saying the force of 15 tons is what we experience when we're 4,000 miles from the radius of the Earth. I say we, I just mean the space module. And so that gives me this constant where x is, again, the distance between the module and the center of the Earth. So let's do that. Let's calculate some work. How much work is done in propelling that module to a height of 62 miles above the Earth? By the way, 62 miles is a roughly speaking, that would be what we consider into space. And then how much work is done in propelling the module to a height of 250 miles above the Earth? And again, that's about roughly where the International Space Station is. So to get to outer space, roughly, that's about 62 miles. And to get to where the International Space Station is, that's about 250 miles above the Earth. So we'll calculate both of these. If you want to try this on your own, obviously try this on your own. Let's do this first one. How much work to get this thing into space, like official into space? Well, the force function is going to be that function we had earlier, 240 million divided by x squared. When I propel it to a height 62 miles above the Earth, be careful here. Remember, the x was the amount from the center. So we're still starting at 4,000 miles away from the center. And we would propel it to a distance of 4,062 miles above the center. So above the outer crust of the Earth is 4,062 miles above the center of the Earth. So we can type this into our calculator. You could also do this by hand if you like. It doesn't matter which way you do it. I don't care which way you do it, whether it's by hand or whether it's by utilizing the definite integration tools on your calculator. And this will be an approximate, I got approximately 915.81. Now this is in miles and my weight was in tons, so this is in mile tons. You could convert that to foot pounds or inch pounds, or if you wanted to, you can convert that to any other thing as well. But right now, since we are using mile tons, I'll use mile tons. 915.81 mile tons of work to propel that space module into what we call outer space. If I'm propelling it into the height of the International Space Station, again, these are rough heights. Well, since the International Space Station is 250 miles above the surface of the Earth, that means it is 4,250 miles above the center of the Earth. So all we do is we integrate from 4,000 to 4,250. Take my force function of 240 million divided by x squared and come up with that number. The number is going to be 3,529.41 mile tons. Again, I wrote equal. I should have said approximately. That is how we can calculate the amount of work. And then obviously from that, knowing the amount of work that has to be done, you can calculate amounts of fuel that are needed and all of those things. So that's what we get for these two problems. Let's do another example. In this example, it says a satellite weighs 2.5 tons on the surface of Earth's moon. Find a force function for propelling the satellite away from the moon. Use 1,080 miles as the radius of the moon. And then it's going to ask us to propel the satellite away from the moon a certain number of miles. But first, let's find the force function. So the force function, we're going to be finding it in a very similar way, although I have to use 1,080 miles as the radius of the moon. That's approximately right if you look that up. So x here is going to be the amount or the distance away from the center of the moon. That means my force function, just like last time, is going to be, I'm going to write it as some constant divided by x squared, because I can combine all three of those constants in Newton's law of universal gravitation. I know that this satellite weighs 2.5 tons on the surface of the moon, and I know that the moon is 1,080 miles, or has a radius of 1,080 miles. That means I can find the constant in this force function by taking 2.5 times 1,080 squared. We're squaring the 1,080 before multiplying by the 2.5. That gives me a constant of 2,916,000, which means that my force function is that number, 2,916,000 divided by x squared. So that's the force function for this problem. And now we can use this force function in order to calculate how much work is done by propelling this satellite away from the moon. So let's calculate how much work is done in propelling the satellite that is on the moon 62 miles away from the moon. And then let's calculate how much work is done in propelling the satellite 238,900 miles away from the moon. By the way, that would be the distance from the moon to the Earth, this number. So we'll just calculate that force as it applies to the moon. So let's go ahead and do that. This satellite had the force function of 2,916,000 divided by x squared. X, remember, was the distance to the center of the moon, which was started at 1,080. And if we were propelling it 62 miles away, we'd have to add 62 to that 1,080, which would be 1,142. That is what my integration is going to be. And obviously, we can just use our calculator just like usual. I ended up with 146.5 0.58. Again, this is in miles and tons, so this would be in mile tons. Notice how much less work is done propelling a satellite 62 miles away from the moon. And the interesting thing is, this was the same satellite because it turns out if something weighs about 15 tons on the surface of the Earth, it would weigh 1/6 of the amount, roughly, on the moon. So that's about 2.5 tons on the surface of the moon. So this is the same satellite that required us to do 915.81 mile tons of work, propelling it 62 miles above the Earth. If I propel it 62 miles above the moon, I'm only required this amount of work, 146.58 mile tons. Now you may say that's fine, but the Earth and Moon are very far away. Let's see how much work would be done in shooting the satellite off the surface of the moon to a distance away from the moon, which is equivalent to the distance to the Earth. Oh, I apologize. That was a rounded number. If I didn't get that. So that was a rounded number. So let's do that. Let's propel it 238,900 miles away from the moon. So it's on the moon, and we're going to shoot it out that far. We're going to start at 1,080. And if I shoot it out 238,900 miles away, then that's an additional 238,900. That means my end destination is 239,980 miles away from the center of the moon. This one, again, you can either do by hand, or what I'm going to do is I'm going to type it into my calculator. As I do that, it'll take my calculator just a second because those are pretty big numbers, but we get 2,600, or at least this is what I got, 2,687.85 mile tons. Interestingly enough, what that's telling us is that without any other factors, it's actually much easier a lot less work is done shooting something from the moon to the International Space Station than it is shooting it from the surface of the Earth to the International Space Station. Less work is done, even though the International Space Station is much, much closer to the Earth. It takes a lot more force to get off of the surface of the Earth because the Earth is that much bigger than the moon. So it takes less work shooting something from the moon to the International Space Station than it does shooting it from the Earth to the International Space Station. Interestingly enough. And I did a single work calculation. I didn't I didn't factor in the gravity of the Earth pulling that module once it gets close either. So there we go. There are a lot of other ways and other scenarios that we could find forces for, and therefore we could find work. We could calculate the work for. But in this class, we're only going to look at these three. And we only did look at these three, where we're just pulling things up or compressing or stretching a spring or shooting something off the surface of the Earth or the surface of the moon. And so that is all we're going to look at in this section. We used integration to calculate work. And again, work there was the physics idea of work. Force times distance.